All right, welcome back to our lesson on the sine and cosine. In the last video, we used shadows to estimate the values of sine and cosine. Now we're going to try to get a handle on how accurate those estimates were. My first approach is just going to be to draw some triangles on my sheet of paper and measure them as accurately as possible. Okay, so I've drawn three angles, a 15-degree angle, a 30-degree angle, and a 45-degree angle. And that might not seem enough since I want to actually check the values of 7 different angles here, but it turns out this will be enough, and you'll see why as we move through it. First of all, I don't really have to worry about the 0-degree option because it's clear to me that when I'm at 0 degrees, my rise is going to be 0, right? I'm level. And my run is going to be 1. It's the whole unit. So I don't have to worry about that case. So let's start with this 15-degree situation. And I have dropped a perpendicular. This length right here, I've made a right triangle, and this length here is 1 unit. Okay, it's 100 millimeters once again, and it's 1 unit. So I'll use millimeters to take my measurements. Okay, so the sine is what happens when you project to the wall. So the sine is the rise, right? It's because we're only taking the rise of this 1 unit. We don't care about what's going on past this 1 unit. So what's the rise of the 1 unit? Let's put our ruler right here. And this looks like 26 millimeters to me. So we're going to write 0.26 for 26 millimeters. That's the sine of 15 degrees. Now let's go over here and let's find out what the run is, the cosine. All right, and that looks to me like, it's between 96 and 97. But it looks a little bit closer to 97. So I'm going to say that the run is 0.97. Now let's turn to this one here. For 30 degrees, my rise, and once again, this length right here is 1 unit, 100 millimeters. My rise, and oh, that looks like pretty much exactly 50 millimeters to me. So we're going to say this is 0.5 units. And then we go over here and we measure the run. And let's see, that looks like 80, it's between 86 and 87 millimeters. It's closer to 87. So if I round to the nearest millimeter, I'm going to call this 0.87 as my run, my cosine. And now let's go on to the 45-degree angle. And here we expect the two to be the same. And let's see, if I go to the top there, I get a measurement that's about 71 millimeters. So 0.71. Once again, I'll specify that this is 1 unit length. And now let's measure the run of the 45-degree angle. Yeah, so we want it to be the same. This one actually looks like it might be right between 70 and 71, almost halfway in between. So let's just give ourselves the benefit of the doubt and say they are the same. So it looked like it was about halfway. We'll go ahead and give it the same value. Okay, so we see the sine of 15 is 0.26. Let's go over here. Sine of 15, 0.26. Oh, I'm sorry, you probably couldn't see that. So for 15 degrees, the sine, the rise, is 0.26, and we got 0.26 from the shadow. For 30 degrees, we see it's 0.5. We got 0.51, so off by about 1 millimeter. And for the 45-degree angle, we see it's 0.71, and we got 0.72 with a shadow. So again, off by 1 millimeter. Now, you might say, well, what about the other angles? But hang on a second. Remember that symmetry between sine and cosine? Well, basically what happened was the sine of 15 degrees was the same as the cosine of 75 degrees. It seemed like it should be, at least, and vice versa. The sine of 75 was the same as the cosine of 0.9. Sorry, the sine of 75 was the same as the cosine of 15. Well, what that would suggest is that if I just rotate this here, this is a 15-degree angle, and then this one down here, well, that should be the 75-degree angle, and then the sine would be 0.97. So the sine of 75 degrees should be 0.97, and sure enough, that is what we got on this table. Let's do the same trick here. Okay, so this is 60 degrees then, and the sine of 60 degrees, the rise, is 0.87. Let's check. We got 0.88, so off by 1 millimeter. And finally, here, we expect it to be the same, and if it is, well, then this must also be a 45-degree angle, right? So we got 0.71, and once again, we already pointed out, off by 1 millimeter. But this is kind of interesting, this fact that when I take this, you know, I think about the sine of 15 degrees, then I just rotate it like this, and I say, oh, wait, this angle must be 75 because of that symmetry. Well, remember in the last lesson, we made this assumption that all right triangles would have the same angle sum. Well, this would sort of give us a clue as to what that angle sum should be, right? Because we know this is a right angle, it's 90 degrees. And this angle plus this angle, well, let's see, these add up to 90 degrees as well. 90 plus 90 is 180 degrees. Let's check it again here. 30 plus 60 is 90 plus 90, 180 degrees. And once again, 45 plus 45, 90 plus 90, 180 degrees. So it looks like if we make that assumption that all right triangles have the same angle sum, that this sine and cosine information would suggest to us, would imply that that angle sum must be 180 degrees. Okay, so this seems interesting, but before we get ahead of ourselves, you may have been told that the angle sum of any triangle is 180 degrees, and this claim is something that we will spend a lot of time on in this particular course, this idea of the angle sum of a triangle. Not as much in this unit, but over the course, we'll spend a lot of time on this question of the angle sum of a triangle. Let's be very clear here. Okay, what I'm showing you here with this sort of complement and symmetry of the sine and the cosine, this is not a proof that the angle sum of a triangle is 180 degrees. Okay, proofs like that will come later in the course, but this is sort of a suggestion based on what we're seeing, based on some symmetries and relationships. This is a suggestion, but it's not a proof. So keep that in mind. Okay, so before we wrap up the video, let's think about how accurate these numbers actually were. I would imagine that these numbers are probably more accurate than this because the shadow, could be a little finicky. Maybe the light wasn't coming in at the exact perpendicular or horizontal angle. So we'll imagine that these are a bit closer. But since sine and cosine and tangent are such useful measurement tools, of course, people have already calculated all the values for all the degrees. And so let's just grab a table. So here is my table of different values of sine, cosine, and tangent. And let's actually zoom in a bit on this so you can see it better. Maybe zoom in even a bit more. Okay, so we have a column for sine, column for cosine, column for tangent. And turns out that sure enough, when we have 0 degrees, we're right on. Sine is 0, cosine is 1, tangent is 0. That's exactly what we said right here. Let's go to 15 degrees. And we see with 15 degrees, if we round to the tenths place, to the nearest sort of millimeter in our unit that we used, we would get 0.26. And hey, that's good. That's right on. So 0.26 is correct. And then 0.97 if we round off for the cosine. And once again, yeah, we got it. So that turned out pretty nicely. Now let's go to 30 degrees. Let's see. So here you can see it. Now this first column is the sine. It says 0.5. We got 0.51, although when we did the 60 degree cosine, we did get to 0.5. So pretty close, off by 1 millimeter. And by the way, we were correct with this triangle right here at 0.5. And 30 degrees, the cosine is, let's see, 0.866. So that would round to 0.87 if we're rounding to the nearest hundredths place. And if we look here, we were off by, again, 1 millimeter. And if we look here, let's see, 0.87, the cosine. Yeah, so we're basically right there. Okay, so I'm not going to go through all these values with you, but the point that I want to show you is, this is a value of trig tables rounded to 4 decimal places. And so these are pretty precise. And the numbers that we got by making triangles and measuring them, and by the shadow method, yeah, they're pretty good. We could take these values and we could, go to a calculator and use the calculator to find all these values as well. And that would take more time. But I'm not going to actually do that because it's the same as looking them up on a table, right? Like just imagine that the calculator knows all these values that we have here on this table. It can give us more decimal places if we want that. But yeah, I just want to make that point that, what we got with the shadows and measuring the triangles is representative of the actual values that have been calculated by, computers, calculators, what have you. Okay, so that wraps up this video, but we're not done with the lesson. In the next lesson, we'll look at a definition, a more proper definition for sine, cosine, and tangent. All right, we'll see you then. Bye-bye.